Now in our bipolar junction transistor. Our first topic is the construction, operation, and configuration. It was on December 23, 1947 that Dr. H. William Shockley, Walter H. Bratton, and John Barden demonstrated the amplifying action of the first transistor at the Bell laboratories. The first transistor was called a point contact transistor, which was the predecessor to the junction transistor developed by William Shockley. The advantage of this three-terminal solid-state device over the vacuum tubes are the following. It is smaller and lightweight. It needs no heater to start up the device. It is rugged construction. It absorbs less power. Instantly available for use. No warming up. And it has a low operating voltages. Transistors are categorized into three. The first one is the general purpose or small signal transistor, generally used for low or medium power amplifiers or switching circuits. So these are the packages of this general purpose or small signal transistor. It is made up of plastic or metal cases. And we have also the multiple transistor packages. The second one is the power transistor, used to handle large currents, typically more than 1 ampere, and or large voltages. So these are the packages of your power transistor. And the third one is the RF transistor, designed to operate at extremely high frequencies and are commonly used for various purposes in communication system and other high-frequency application. And these are your packages of an RF transistor. This bipolar junction transistor is a three-terminal device and consists of three layers. Two of them are doped to a one-type semiconductor and one the opposite. The three layers are called the collector, base, and emitter. We have an NPN. It means that your collector is doped with the negative material together with your emitter. And your base is the opposite material that will be your positive. For the PNP, your collector and emitter are doped with the same material that is positive, and your base is the opposite that is your negative. And this is the symbol of your NPN and PNP. The emitter side has an arrow. So this is how to determine if it is an emitter. So it has an arrow. If it is pointed outside from the transistor, it is an NPN. If it is pointed going to the transistor, it is PNP. So the terminal are the emitter, base, and collector. And this is the dimension of your three-terminal device. We have a 0.15 of an inch, the entire device, where 0.001 is for your base. So it is a too small area of your device. It is a thin size area. So there are two types. We have the NPN. So NPN, the collector and emitter have the same type. So since it is NPN, so it has an N type, and the base region is your opposite, that will be your P type. For the PNP, the collector and emitter regions have the same type, that is positive, and the base region will be the opposite, and it is your negative type. So emitter, it is a portion of one side of the transistor that supplies charge carriers. So these charge carriers is either electrons or holes to other portion, and it is heavily doped region. Emitter of PNP transistor supply holes charged to its junction with the base, And if it is a NPN, it supplies free electrons to its junction with the base. For the collector, it is a portion on the other side of the transistor that is opposite to your emitter, and this will collect the charge carriers. It's either electrons and holes. Remember, emitter supplies, collectors will collect the charge carriers. The doping level of the collector it is between the heavily doping of emitter and the light doping of the base. So the base is a middle portion which forms the 2p junction between emitter and collector. It is thin as compared to the emitter and is slightly doped portion. The function of the base is to control the flow of charge carrier. So to recall, emitter, supply, collector, collect, and base to control. So there are two junctions in the bipolar junction transistor. We have the emitter base junction and the collector base junction. Each junction can either be forward bias or reverse bias, and there are four distinct regions of operation. We have the active or forward active or simply active. We have the reverse active or inverted. We have the saturation and the cutoff. So this is the table on your junction bias for your emitter base junction or collector base junction, and the mode of operation based on the applied voltages for the terminal. It's either emitter base or collector for your NPN and your PNP. So what is a forward active? The base emitter junction is forward bias and the base collector junction is reverse bias. Most bipolar junction transistors are designed to afford the greatest common emitter current gain, which is called beta in forward active region. The collector emitter current is approximately proportional to the base current, but many times larger for small base current variation. The bipolar junction transistor can be used as an amplifier and in analog circuit. For the reverse active, the base emitter junction is reverse bias and the base collector junction is forward bias. So this mode is the emitter and collector region switch rule. Since most bipolar junction transistors are designed to maximize current gain in forward active mode, the beta in inverted mode is several times smaller. This mode is seldom used, usually being considered only for fail-safe condition and some type of bipolar logic. For saturation, with both junctions are forward bias. Large collector current flows to the emitter and a small voltage across collector base junction. These modes behave as a closed switch. And the last one is cutoff when both junctions are reverse bias. In this situation, there is nearly zero current and the transistor behaves as an open circuit. The operation of the PNP transistor is extremely same if the roles played by the electron and the hole are interchanged. The PNP region or PNP transistor has been redrawn without the base to collector bias. Note the similarities between this situation and that of a forward bias diode. Remember, in our forward bias diode, the depletion region has been reduced in width due to the applied bias, resulting in a heavy flow of majority carriers from the P to the N material. Now, let us remove the base emitter bias And consider this by putting a reverse bias of your collector to base. So as you can recall also in your reverse bias diode that the majority carriers is zero, resulting only to the minority carrier flow. So if we have to combine these two with external sources BEE and BCC connected, so both biasing potential have been applied to the PNP transistor with resulting a majority and minority carriers flow indicated in the figure. Note the width of the depletion region, indicating clearly which junction is forward bias and which is reverse bias. As indicated also, a large number of majority carriers will diffuse across the forward bias PN junction into the N-type material. The question then is whether this carrier will contribute directly to the base current or pass directly to the P material to your collector. Since the sandwich N-type material or your base region is very thin and has a low conductivity, a very small number of these carriers will take this path to the high resistance of the base terminal. The large number of these majority carriers will diffuse across the reverse bias junction into the P-type material which is connected to the collector. So the reason for the relative ease with which the majority carriers can cross the reverse bias junction is easily understood if we consider that for the reverse bias diode that the injected majority carriers will appear as minority carriers in the N-type material. In other words, there has been an injection of minority carriers into the N-type base region material. Combining this with the fact that all the majority carriers in the depletion region will cross the reverse bias junction of a diode accounts for the flow as indicated in the figure. So then we have to get the current of the transistor. As you can recall that the majority carriers will go from your emitter going to your collector, and there is only a small amount of this carrier going to your base. So if we have to apply the Kirchhoff's current law, the emitter current is the sum of the collector and base current. So therefore, IE is equals to IC plus IB. And remember also that the collector current is composed of two currents. We have the majority and the minority. The minority is what you call your ICBO. So it means that it is this time that your emitter is open. So we have what you call your collector to base current emitter is open. That is also the same or applicable to your NPN type of bipolar junction transistor. So for the configuration of a common base, we have this one. We have a base is common to both input, which is our emitter, and to our output, which is our collector. So we have the NPN and the PNP type. So for the PNP, your input current will go to your directly to your transistor, and your collector current will go out from your transistor. Whereas for the NPN type, your input current will go out from your transistor, whereas your output current will go into your transistor. So these are your characteristic of your common base configuration. This gives you the relationship between the input current or IE to the input voltage, which is your voltage base emitter, for three output voltage BCB levels. So if we have your BCB increases to 20 from 1, your input voltage VBE is the same. So we call that one in your diode topic, it is what you call your knee voltage. So for silicon, it is approximately zero point 0.7, and for germanium, that is zero point 0.3 volts. But germanium is seldom used as a material in making a bipolar junction transistor. Usually, it is as silicon. So for the output characteristic, this graph demonstrates the output IC to an input voltage BCB for various level of your input current IE. So in the DC mode of levels of IC and IE, due to the majority carriers are related by a quantity called alpha, and it is a ratio between your output over your input. And this alpha must be less than or equals to 1. Since alpha is defined solely for the majority carriers, so therefore IC is equals to your alpha IE plus ICBO. But since ICBO is too small to be considered, then therefore IC is equals to alpha IE. So the operating region, we have the active. It is the operating range of the amplifier. It is noticed that IE is approximately equals to IC. For cutoff, it is an operating condition of the transistor R0 input base current or IB equals to 0 and 0 output collector current or IC equals to 0 and maximum collector voltage or that is what you call your BCE, which result in a large depletion layer and no current flowing through the device. Therefore, the transistor is switched fully off. Then for saturation, the transistor will be biased so that the maximum amount of base current is applied, resulting in a maximum collector current and also resulting in the minimum collector emitter voltage drop, which result in the depletion layer being as small as possible and the maximum current flowing through the transistor. Therefore, the transistor is switched fully on. For the common emitter configuration, we have this one. So your common is emitter, your input now is your base, and the same output is the collector. So we have this notation symbol for the common emitter as an NPN and the PNP transistor. This is your collector characteristic, and this is the base characteristic with the 3 level of your BCE. And the ratio between your collector or your output over your input is what you call your beta. And beta is equals to IC over IB. And that's all for our lecture number 1, which is the construction, operation, and configuration.